Hello, I am Sarvesh, and today I am going to talk about what is dining philosopher's problem, which is a classical synchronization problem in operating systems. Let's take a look at it. Now, first I am going to introduce the problem. First, the dining philosopher problem was proposed by Edsel Disaster in 1965 to illustrate synchronization issue in operating system. The problem states that suppose if five philosophers sit around a table alternating between eating and thinking, a fork or a chopstick is placed between each pair of philosophers, making five in total. Now each philosophers need to pick two forks or two chopsticks left or right to eat. If each philosopher picks left fork at the same time, they each end up with right for waiting for the right fork, which causes a deadlock. Let's take an example. Suppose here is a philosopher, here are chopsticks, and suppose everyone picks their left, that is P1, philosopher once picks up chopstick C1. So therefore, if each philosopher picks five chopsticks of their left side, they end up waiting for their right side, causing a deadlock. Now, what are the core issues to understand this problem more clearly in operating system? First of all, what is a deadlock? All philosophers pick up one fork and wait forever for other, resulting no progress. Second is starvation. One or more philosophers might never get a chance to eat due to unfair resource access. Concurrency, multiple philosopher processes or attempts to access shared folks resources, leading to conflicts. Meaning all philosophers are trying to access shared resources, but it can be only picked by one. This simulates real-world problem in operating system. For example, memory management, printing, files, and other shared components that can be usually used by one entity or one device. Now, what are the conditions for deadlock? For a deadlock to occur, these four conditions are must, not three, not two, not one. These four conditions are must for a deadlock. Okay, let's go it one by one. What is mutual exclusion? Suppose a resource can only be used by one process at a time. This is the condition one of deadlock as I explained earlier. Now hold and wait. A process is holding on to at least one resources and waiting for others. Meaning, if a philosopher has one chopsticks and he is waiting for the left or right, either one of them for the resource. Now here the chopsticks is a resource. Now third, no preemption. It means our philosophers can't forcefully take the chopsticks from other philosophers' hand. Now circular wait, a set of processes waiting for each other in a circular chain. We have already taken example here. Suppose everyone pick their left chopsticks, they will wait for the right one, causing a circular wait. Now to prevent deadlock, we must break down at least one of these conditions. Okay, what are the popular solutions for the dining philosopher's problem? Let's take an example or the solution. Resource hierarchy. Assign number to folks and require philosophers to pick them in order. Lower number first. Suppose philosopher 1 picks chopstick 0 and 1. So, eliminating the condition for deadlock. Okay, or we can limit the access. Allow only 4 philosophers to attempt eating at same time, ensuring one fork is always free. So, if there are 4 philosophers and chopsticks number are 5. So we can assume that if one philosophers get two chopsticks and he is going to eat and think. After completion, he can free up the chopsticks. So we can make sure at least one philosopher is getting the chopsticks. So it can prevent deadlock. Now, what is central waiter? Introduce a waiter to control fork access. Philosopher must ask before picking up forks. This is similar to a mutual exclusion in which only one philosopher can pick up the chopsticks. Now, asymmetric strategy. Some philosopher picks the right one, some philosopher pick the left one, causing circular weight or deadlock chain to break. Now, what are the real applications which may be implied on operating system? Let's take an example. Suppose applications include operating system managing memory, printers, or thread. Let's take an example of printer. Suppose I give print command to print a docx file, and other one also gives to print docx file. But there are two operations and the printer can only print one operation. So it stacks up and prints one by one, operating all the commands. Now database handling simultaneously access to records. Suppose we know all that airlines use common databases, so they need concurrent access or simultaneous access to records. That's why dining philosopher plays an important role and which helps to synchronize the system and share in a shared resource manner. Next, network system managing shared bandwidth or path. We also use internet. We can access the internet concurrently and many users across worldwide simultaneously. Now, what's the takeaway from dining philosopher's problem? It is a core principle or core operating system concepts which explains OS concepts like resource sharing, deadlock prevention, and synchronization. The takeaway is that safe resource allocated is essential. Thinking smartly, coordinating resources, and avoiding greedy behavior to prevent a deadlock, just like well-behaved philosophers. That's why it is called a dining philosopher's problem, because philosophers are smart.